Welcome back to the podcast. Today, we're diving deep into a fascinating new paper from a team at UCLA and Lawrence Livermore National Laboratory, spearheaded by Eric Jiang and a host of collaborators, including the renowned Terence Tao. The paper, titled From Solvers to Research, Large Language Model-Driven Formal Mathematics at the Research Frontier, lays out a compelling vision for the future of AI in mathematics. For a long time, AI for mathematics, or AI for math, has focused on building systems that can reason formally. Early approaches, like neural symbolic methods, aim to combine pattern recognition with structured logic. They achieved some notable success in high-accuracy proof synthesis within formal environments. But these methods often relied on fixed, manually designed heuristics, which limited their scalability and applicability across diverse mathematical domains. Essentially, they were good at problems within their predefined scope, but struggled to generalize.
So, these early systems were like specialized calculators, effective for specific problem sets but lacking broader mathematical intuition. How did the emergence of large language models, or LLMs, change this landscape, especially with their reputation for more generalized understanding?
That's a sharp distinction. LLMs brought a significant shift. Models like DeepSeek, R1 and the O series, as the paper mentions, have demonstrated strong performance on various benchmarks involving informal mathematical reasoning, meaning math expressed in natural language. They can solve a substantial fraction of undergraduate math problems just through in-context reasoning, even though they were primarily trained on general text corpora. This was a surprising emergent capability, as seen with models like GPT-4, Claude, Gemini, and Llama.
An interesting point about these general-purpose LLMs is their emergent capabilities. But when we talk about mathematics, especially at the research frontier, precision is paramount. If these models are reasoning informally, how do they handle the inherent risk of hallucination, which is a known challenge with LLMs? Mathematical research demands absolute rigor.
You've hit on the core limitation. While informal reasoning with LLMs is impressive, their outputs lack precise, machine-checkable semantics. This makes them prone to hallucination, as you noted, and precludes autonomous verification. And autonomous verification is a prerequisite for tackling open-ended mathematical research, where a false step can invalidate an entire line of inquiry. This is where interactive theorem provers, or ITPs, come into play. The research has actively pivoted towards LLM-driven formal mathematical reasoning systems. By integrating LLMs with IDPs like Lean, which provides rigorous verification, systems such as DeepSeek Prover and Seed Prover have set new standards. They're generating formal proofs in competition-level mathematics. The paper even highlights hybrid approaches that combine LLMs with geometrical deduction engines, which have surpassed human gold medal performance on International Mathematical Olympiad, or IMO, geometry problems. This is a significant leap beyond just informal reasoning.
So, the key is this synergy, LLMs providing the reasoning and IDPs providing the unimpeachable verification. But what exactly are these interactive theorem provers? How do they function as the rigorous backbone for LLM-generated proofs? I'm particularly interested in what makes an IDP like Lean suitable for this task, especially compared to earlier systems.
That's a crucial question. IDPs are software systems that allow users to construct and check formal mathematical proofs. They enforce a strict logical framework, ensuring every step of a proof is sound and verifiable by the machine. Think of them as extremely pedantic, but absolutely reliable, proof assistants. The paper provides a table comparing several ITPs, including Isabelle, Coq, HLLite, MetaMath, and Lean4. Isabelle, for instance, first released in 1986, is built on higher-order logic and uses a tactic proof style, with high automation through tools like Sledgehammer. It has an extensive library, the archive of formal proofs, with over 5 million lines of code. Coq, from 1989, uses the calculus of inductive constructions, also supporting tactic and term-style proofs. HLLite, from 1996, is another higher-order logic system. MetaMath, a bit newer from 2005, is based on set theory and uses a term-style proof. Lean4, however, is a more recent player, first released in 2021. It also uses the calculus of inductive constructions and a tactic-proof style, but it boasts the MathLib library with an impressive 1.9 million lines of code. What's notable about Lean 4 is its modern design and active development, making it a very strong candidate for LLM integration supported by systems like LeanDojo.
The sheer scale of these libraries, like MathLib with 1.9 million lines of code, suggests a massive repository of formalized mathematical knowledge. My question then is, what's the human learning curve for these IDPs, especially Lean 4? Are they accessible enough for mathematicians to use them effectively, or do LLMs offer a way to bridge this expertise gap, acting as an interpreter or an expert user?
That's a critical point. Historically, learning to use an IDP has been a significant barrier. It requires not just mathematical expertise, but also proficiency in a specific formal language and its proof-writing methodology. It's often compared to learning a new programming language specifically for proofs. LLMs offer a pathway to democratize this. Instead of a human writing every formal line, an LLM can generate the formal code or proof tactics, which the IDP then verifies. This shifts the human's role from low-level formal coding to high-level guidance and problem formulation. So, in essence, the LLM acts as an expert formalizer and prover, interacting with the IDP. The paper distinguishes between general-purpose LLMs and those specialized for mathematical reasoning. While models like GPT-4 show surprising capabilities, dedicated foundation models for mathematics are being developed. These specialized models are not just fine-tuned versions of general LLMs. They often incorporate architectural designs or training methodologies specifically geared towards the nuances of mathematical structures and reasoning. This specialization is crucial for moving beyond undergraduate-level problems.
If these specialized LLMs are designed to integrate with IDPs, what does this specialization specifically entail? Is it primarily about better autoformalization, translating natural language problems into the precise syntax of an IDP? Or does it also extend to the strategy of proof generation, navigating the vast search space of possible mathematical deductions?
It's both, and autoformalization is indeed a monumental task, as it's the bridge between human intuition and machine rigor. The paper highlights this semantic gap. Consider a familiar theorem. Every continuous function on a closed interval attains its maximum. To a mathematician, that's unambiguous. But a formalization in Lean 4, for instance, requires making numerous implicit assumptions explicit. You need to define the function type, the real numbers, the closed interval, continuity, and the existence of a maximum within that interval, all in a precisely machine-checkable way. For example, the Lean 4 formalization for that simple statement could look like theorem continuous underscore attains underscore max f. RR, AB. R, H1, A less than or equal to B. H2, continuous on F, ICCAB. There exists X is an element of ICCAB, for all Y is an element of CAB, F, Y less than or equal to Fx. This requires defining continuous on, ICC, closed interval, and existential quantifiers for the maximum. Autoformalization means the LLM generates this precise, structured code from the informal sentence. It's not just syntax, it's deep semantic translation that captures all implied logical constraints.
That example clarifies the complexity. It's far more than just converting words into symbols, it's about making implicit mathematical axioms and conditions explicit. What are the common failure modes in this autoformalization process? Does the AI often misinterpret the scope of variables, or omit crucial domain constraints, leading to incorrect or unprovable formal statements?
Exactly. The paper details several failure modes. A big one is implicit quantification and domain constraints, as in our continuous function example. Another is ambiguous terminology or notation in informal math, where a symbol might have multiple meanings that need disambiguation in a formal system. LLMs can misinterpret context or fail to select the correct formal definition. This can lead to a formal statement that is either not equivalent to the original informal statement or is outright ill-formed within the ITP's logic. Measuring success isn't just about textual similarity. It's about semantic equivalence. formally verifying that the generated statement logically implies the reference. Once a problem is formalized, the LLM then engages in proof synthesis. This is where the LLM generates the actual sequence of logical steps and tactics within the IDP to construct a proof. The paper shows an example from Lean 4. For a problem like, if real numbers x and y satisfy 0, x less than or equal to 1/2, and y sin x, then y less than 1/2. The LLM might generate a proof sketch with hints, then refine it into a full formal proof. It uses lean tactics like exact, sin_lth2, .love4 sin x equals x, given x 0, and t.trans_h3 for y less than x, given y sin x and sin x equals x. Finally, linearith is a powerful tactic that solves linear arithmetic goals. So, the LLM isn't just translating. It's actively performing deductions, choosing appropriate tactics, and building the proof step by step under the rigorous oversight of Lean.
So the LLM is acting as a sophisticated, automated proof assistant, not just a translator. Does this imply a recursive or iterative process, where the LLM proposes a step, gets feedback from the IDP, and then refines its approach? Or is it more of a one-shot generation that is then checked?
It's definitely an iterative and often recursive process. Modern systems like DeepSeek Prover and Seed Prover often employ search strategies, sometimes combining tree search with LLM-generated proposals. They'll generate multiple proof attempts, evaluate them based on IDP feedback, e.g., if a step type checks, or if a tactic successfully closes a goal, and then refine their strategy. This feedback loop is essential for debugging and guiding the LLM towards a valid proof. The paper even touches on metacognitive capabilities of LLMs in mathematical problem solving, implying an internal evaluation mechanism. The results of these integrated systems are quite striking, especially in competitive math. Looking at the IMO 2025 results table, systems like Seed Prover, Gemini Deep Think, IMO Gold, and a GPT-5 experimental version all achieved 83.3% accuracy, scoring 35 out of 42 points. They solved problems P1-5. For IMO 2024, Gemini Deep Think again scored 76.2%, and AlphaProof reached 67%, equivalent to a silver medal. These are not trivial problems. They're designed to test advanced mathematical insight and creativity.
Achieving silver medal equivalent performance on the IMO is undeniably impressive, demonstrating a high degree of problem-solving capability. However, as you alluded to earlier, IMO problems, while challenging, are still well-defined. The paper's core argument is about moving towards frontier research. Are these current systems merely powerful solvers of predefined problems, or are they showing early signs of genuine mathematical discovery?
That's precisely the distinction the paper emphasizes. While current systems excel at solving well-defined problems, they remain fundamentally limited in tackling frontier research mathematics. The paper identifies several core limitations preventing them from acting as true mathematical research agents. First, the datasets. Existing datasets, while extensive, often lack the open-ended, underspecified problems common in research. Second, relational structure. LLMs can struggle with non-local dependencies and high-level structural understanding across complex proofs. Third, mathematical exploration. They don't yet effectively explore novel ideas, propose new conjectures, or identify promising research directions autonomously. Furthermore, there are gaps in the tool ecosystem, and the nature of human-AI collaboration needs to evolve. For instance, when it comes to exploration, an AI might be able to generate many valid proofs for an existing theorem, but it struggles to formulate a new hypothesis that could lead to a novel theorem. It's like having a brilliant student who can ace any exam but struggles to formulate a unique research question for their thesis.
The relational structure limitation for LLMs is particularly concerning for advanced mathematics. If they struggle with non-local dependencies, it suggests a fundamental difficulty in grasping the intricate, interconnected concepts that form the fabric of complex theories. Does this imply a lack of what we might call deep understanding beyond superficial pattern matching, and how might that be addressed?
It strongly suggests that. While LLMs are excellent at local coherence and sequential reasoning, their ability to maintain and reason about complex, non-local relationships across a vast mathematical landscape is still developing. Addressing this might involve new architectures that explicitly model hierarchical or graph-like relationships within mathematical statements, rather than treating them as flat sequences of tokens. It also involves training on datasets specifically designed to highlight these deep relational structures, rather than just proof steps. The paper outlines a strategic roadmap to overcome these limitations, advocating a decisive shift from predefined problem solvers to genuine research agents. This means developing systems that can address frontier mathematical challenges with rigorous formal reasoning. The goal is to tackle problems that are open-ended, underspecified, and involve multiple layers of abstraction. This isn't about just finding a proof for a theorem. It's about discovering the theorem itself or resolving an open conjecture.
A shift towards research agents implies a far more proactive and creative role for AI. What concrete architectural or methodological innovations are needed for this? Does it require a shift from primarily supervised learning on existing proofs to more unsupervised or reinforcement learning paradigms that encourage exploration and hypothesis generation?
Precisely. It calls for fundamental changes. Beyond supervised learning on existing proofs, it necessitates frameworks that support true mathematical exploration, similar to how a human mathematician might experiment with ideas. This includes systems that can propose novel testable claims, mutate existing formalizations to explore variations, and then verify these ideas. It also means incorporating more sophisticated meta-reasoning capabilities, allowing the AI to reflect on its own progress and identify fruitful avenues for exploration. Crucially, this vision centers on human-AI collaboration, not replacement. The diagram in the paper illustrates this. An AI can propose a testable mathematical claim, often a conjecture, based on patterns or insights it detects. For example, for an Erdos problem, the AI could propose a specific constant C for an inequality and then try to prove it. If the proof fails or a counterexample is found, the verification feedback informs the AI, leading to a mutation or adjustment at the level of the problem formulation. The human mathematician then reviews, guides, and interprets, forming a symbiotic loop.
The idea of AI proposing conjectures and mutating formalizations is the most exciting and challenging aspect. How does an AI generate a novel conjecture that isn't simply a trivial rearrangement of known theorems? Is it a statistical pattern matching process over large mathematical corpora, or something more akin to a guided search within a conceptual space defined by mathematical structures?
It's likely a combination. Current AI systems are adept at pattern recognition, so they might detect patterns in sequences, primes, or other mathematical objects that suggest a generalized statement. For instance, if they see several specific cases of an inequality holding, they might generalize it and propose a universal constant or a broader condition. Mutation in this context refers to systematic variations of a problem or a conjecture. If an AI proposes mx_1, x_n equals c asterisk 1/n asterisk sum x_I, and it's too strong, a mutation might be to adjust c, or the form of the inequality. The IDP then provides the objective, formal feedback on whether these mutations hold true. The ultimate takeaway is this paradigm shift. We're moving beyond AI systems that simply prove existing theorems. The goal is for AI to actively participate in the discovery process, generating new mathematical knowledge. This includes tackling monumental challenges like Hilbert's problems, the Millennium Prize problems, Landau's problems on prime distribution, or the myriad unsolved problems posed by mathematicians like Erdos. The paper even lists some of these, like Guy's number theory problems or Bondi-Murdy graph theory problems, highlighting the vast landscape of open questions.
So, the vision isn't just about accelerating proof verification, but genuinely expanding the frontier of mathematical knowledge, with AI as a co-researcher. It's about AI contributing to the very questions that define the leading edge of the field, not just answering those already formulated. This is a profound shift from a tool to a partner.
Exactly. The transition from AI as a problem solver to an AI as a research agent signifies a fundamental paradigm shift. We're moving towards AI systems that possess a deeper, more abstract mathematical understanding, enabling novel discoveries and pushing the boundaries of formal mathematics alongside human experts. It promises to augment human ingenuity and accelerate the pace of mathematical progress in ways we are only just beginning to imagine.
Thanks for listening. This has been a truly fascinating look into the evolving landscape of AI and mathematics. The potential for these systems to not just solve but to discover mathematics is a captivating prospect, and we'll certainly be watching closely as these capabilities continue to develop. See you next time.